Electrical impulses are critical signals in the human body, so we need to spend a few minutes talking about what electricity is. Let's get oriented first. Recall that we're now talking about three core concepts in anatomy and physiology: homeostasis, the movement of molecules down gradients, and the relationship between structure and function. Of these, we're now talking about movement of molecules and specifically charged molecules. So the focus today is going to be on electrical gradients and specifically what types of molecules conduct electricity in aqueous solution. The key to electricity is that positive charges are attracted to negative charges. If we have an aqueous solution with sodium chloride in it, the sodium ions dissociate from the chloride ions. Sodium is positively charged, chloride negative, and they're bouncing around randomly in water like the other molecules, but in such a way that the positive charges are a lot more likely to be next to negative charges. If a positive charge approaches another positive charge, there's going to be a repulsive force. So in a saltwater solution, the positive charges and negative charges are next to each other. Something is different if we can separate positive charges from negative charges. If we separate the two, then there's an electrical force that attracts the positive charges on one side to the negative charges on the other. This is called an electrical potential or a voltage. And if we separate more charge, there's a greater force and a greater voltage. Now imagine we have a cell membrane separating these positive and negative charges, and that membrane is preventing the ions from approaching each other. What will happen if we allow the charges to flow? You guessed it, they'll flow towards each other, and the flow of charge is an electrical current. The third type of gradient we commonly deal with in physiology is an electrical gradient, electrical forces, also known as voltage. In this system here, I have a circuit that will light a light bulb. If I connect the circuit, okay, so oops. There are batteries, and the batteries are separate positive charge from negative charge. If I complete the circuit, charges will run through the system, electrons will run through the system and light the bulb. Contrary to popular belief, if I submerge these terminals in water, the water does not conduct electricity. It does not complete the circuit. On the other hand, if I take some table salt, sodium chloride, and put it into the water, dissolve the crystals. Recall that sodium chloride will dissociate in water into positively charged sodium ions, negatively charged chloride ions. And I apply a voltage in this solution. Then there's a dim light there. I'm not sure if you can see that. Okay, but I'll light the bulb in salt water, but not in fresh water. Now let's think, why was the light dimmer when I used the electrolyte solution than when I just connected the bulbs like this? In both cases, the pressure gradient is the same. The voltage produced by the batteries is the same. The difference is the resistance through the electrolyte solution is greater. So even though the pressure is the same, resistance is greater, therefore electrical flow or electric current is less. The voltage will push charged particles from one place to another. Resistance opposes that movement. Now let's do one other demonstration that I think is really important. I've got table sugar here. Glucose is not a charged molecule. Sucrose is not a charged molecule. If I dissolve this substance in water, just like I did the salt, Sucrose will move down its concentration gradient till those molecules are distributed equally throughout this solution. There is a diffusion gradient, diffusion pressure that will move those molecules. But if I use this solution, I'm not going to light that light bulb. No light. Why? Electricity is the movement of charged particles. If there are neutral particles like sugar, there is not going to be an electric gradient. There's no separation of positive and negative charge contributed by the sugar itself. So electric forces will drive positively charged molecules towards negative charges. It will not affect those particles without a charge. Or I should correct that last statement. Particles without a charge might have a more positive and more negative end, so electrostatic forces may affect the orientation of those particles, but it will not cause movement of particles from one point in the solution to another.